Hey everyone, I'm Matthew Spotton. Today I hope to document my journey building an STM32 based oscilloscope. There's a lot that I want to cover, so I'll move quickly, but we'll jump right into it. So if you remember from our first video, I was having challenges with our STM32 oscilloscope being on a prototype board. I wanted to get an actual custom PCB board, but if I was going to go that far, I wanted to make it a little bit better. So I decided to use a different microcontroller that had a little more power, that could sample a little faster and had some other capabilities, alongside the Embedded Oscilloscope software created by Jacob Perez, which really inspired this whole project. Here's the schematics for our oscilloscope. And the first thing to recognize is how I did the dual power supply. It's a little different than on the last one. I decided to use a DC to DC regulator. I take our isolated 5 volts and I regulate it down to 2.7 volts in reference to the negative side of the isolated 5 volts. And then I just reference that 2.7 volts to ground, which creates us a negative 2.7 volts. And then I have the 2.7 volt adjusted regulator for our positive side. If we actually go down, this is the interesting part, I think, is how I chose to do the oscilloscope input processing. So the struggle I was having was finding op amps that could do large input range while not being too expensive. And so I decided to actually go with an input range of 5.5 volts because that still proved to be cost effective. But that didn't allow me the full negative 3.3 to 3.3 volt input range like I wanted. I decided to create a resistor capacitive divider inside the 1 mega ohm input resistor that you find on traditional oscilloscopes. The reason it has to be a capacitive resistor divider is because there's parasitic capacitance in this trace as well as in the op amp input pin. We have to create this capacitive divider with the same gain as the resistor divider so that we don't see any weird effects. But at this point, we don't actually know what the parasitic capacitance is, so we'll have to figure that out during testing, and then we can tune these two values if we need to in order to create a capacitive divider with the same gain. For me, I chose a gain of 0.82 in order to map the signal, because I wanted to get negative 3.3 to 3.3 volts. What's really cool about the setup, though, is if you wanted negative 5 to 5 volts, you could just adjust these capacitor and resistor values, and you'll be able to just do the math and calculate it. And I also chose to separate the 820K resistor between two resistors here. I have a 1.5 mega ohm and a 1.8 mega ohm resistor. The reason I chose to do that is because the second 1.8 mega ohm resistor to ground acts as a DC bias about ground while we're using the AC coupled mode. The next part is we just buffer our signal with the op amp. We map it so it's positive with a resistor divider, and we send that into the next op amp. So now it's at a range from 0 to 2.7 volts. We just have a little higher gain of about 1.2, and that gives us a range of 0 to 3.3 volts. And that's perfect for STM32, so it can read the whole range of its input. I do a couple other things in these schematics that are interesting. I have my clamping circuitry from the other oscilloscope for our counter input. For our signal generator, I do some interesting things. This allows us to output bipolar and unipolar signals. I thought because I had a dual power supply, I might make it possible that we could output a unipolar signal based off of our input. But notice I didn't put a resistor on the output of this op amp to the BNC connector. So there's no series resistor here, and that'll prove to be important later. With these schematics, I designed myself a PCB, being very mindful of proper PCB layout and guidelines. As a side note on PCB layout, in high school I attempted to build a running smartwatch based around an STM32F303 as it has an integrated MIPI controller and is compatible with high-speed parallel PCRAMs. With only 2 layers to squeeze the 47 total signal traces in for the PCRAM, I used vias to cross between the top and bottom layers of the PCB. I didn't understand AC circuits as well then, and the fatal mistake I believe I made was that my high-speed signals changed reference planes without adequate return paths. The return paths for these high-speed signals could not transfer through local shorting vias as my reference planes were at 2 different potentials, power and ground. Instead, they would have to find the nearest decoupling cap acting as a DC block. Because of the large amount of traces, even greater crosstalk would theoretically be introduced by the shared return paths. With this board, I could achieve about 10 MHz before failure, but I was hoping for more and learned. I hope me sharing this helps you in your PCB design journey as well. But with that in mind, I designed my board with the 2 inner planes being ground and ground, connected often with shorting vias, with the top and bottom fill also being ground, and the power traces running on the bottom and the top of the board. Before I actually purchased the PCB, I wanted to try out the hardware. I soldered up this prototype board with the equivalent we saw in the schematics and started doing some testing. The first thing I noticed was that the input of the STM32 is extremely noisy. I assumed it to be the unterminated op amps and decided to go through and terminate each of the op amps with these jumpers, which didn't solve the problem. But needing to get the board purchased, I decided to add series resistance to the output of the op amp and the input of the STM32. And the reason why this worked was because the STM32 pin is capacitive. There's a couple nanofarads of capacitance there, and the trace is also capacitive, and so the op amp trying to derive a capacitive load ends up ringing. And so if we put a series resistor right after the op amp, we end up attenuating that ring and allowing the voltage of the signal to be read. I'm now going to go over my process for assembling the PCBs. This is actually the second board that I made. The first one I made by soldering the SMD components by hand, and that was so much of a pain that I bought myself some new solder paste. And because we don't have a stencil, we just place it on the board pad by pad. And I've organized my components in such a way that they're in line with the bill of materials sheet. We just place all the components for that component. After that, I place the board on a hot plate to apply a constant heat to it, and then I use my hot air gun on top to apply heat and melt the solder. At this point, I solder my STM32 and then all the rest of the through-hole components, and then clip off the extra pins. Now that we have our assembled PCB, we can upload the firmware. I use an ST-Link with the STM32 Cube programmer. I also like to use the ST-Link utility tool, which I find to have more functionality and more control over sector erases and programming, as well as viewing the registers in memory. After we upload the firmware, we can test the board. There's a couple things that need to be tuned. The first thing that I noticed was that the output of the signal generation was noisy. And this is the same problem that we were having with our oscilloscope inputs. I cut the traces on the output of the signal generation op amps and added series resistors, 100 ohm resistors, which solved the problem. We also need to tune the capacitive divider, and I did that by trying different values of capacitance until I got the gain the same. At this point, we can actually calculate the parasitic capacitance. This value is actually only as accurate as the capacitors that we used, and there's all sorts of errors in this calculation. I want to post a more accurate value on my GitHub later, but this is what we're going to use for testing purposes, and then we can tune more specifically from there. As for the oscilloscope case, I designed it with Fusion 360, sliced it with Cura, and then printed the bottom and the top with my Ender 3V2. The PCB is secured to the case with M2 by 4mm screws, and the case is sealed with M2 by 20mm screws. I then use double-sided tape to secure my sticker and optionally add these rubber feet. So as I was working on this project, I started getting really thirsty to code something. I wanted to change the oscilloscope pins to be different than the logic analyzer pins. I also wanted it to be easier for the user to install the software, so to have links and abilities to be able to install it from the device itself. And just anything else I wanted to include in it. So I thought, well, I'll just recompile the firmware because the author included all the source code on his GitHub. In all my efforts to recompile the firmware, I was running into some very unique challenges. I observed that the STM32 is hard faulting as we were trying to start the RTOS scheduler. I created a document to kind of observe what was going on as I discovered and debugged the problem. I came down to realize that the task context block that is initialized at the beginning of the RTOS, I believe, was having the default values but not the correct initialized values after initialization. I think that was causing some hard faults as the addresses were set to invalid addresses. I'm not totally sure though, I was just doing my best to debug it. I also noticed one other thing. The original firmware is 63 kilobytes and my recompiled firmware was 113. If anyone has any idea why that happens, I know that I could have used a different firmware package for the STM32 in CubeMX, as well as a different CubeMX version and maybe different optimization flags or something, but I know the lower optimization flags are code in the comments said not to use because it could break the RTOS. So I have no idea why these are different sizes, and looking at the disassembly, they're completely different. But as I was looking at the disassembly, I started having ideas about what I could do, even though I couldn't recompile the firmware, because I wanted to have the option for the user to have links and resources in order to understand more about the project. My thought process was that I could have a secondary firmware with all of that functionality, and the primary firmware could jump to that secondary firmware. So we can take our working primary firmware and patch it in order to jump to the secondary firmware on the condition that our PC12 pin is set, and there is a boot switch that is connected to the PC12 pin. Before we actually get into patching the firmware, I would like to create the secondary firmware in order that we have a place to jump to and test its functionality and its workability. So to create our secondary binary, we're going to use STM32 CubeMX and put in our microcontroller 303. What I'm doing right now is configuring the clocks and setting the USB device to a mass storage device. Controllers Tech has a great video on this that I'll link. The reason why I wanted to do this is so that the user has some way to interact with our oscilloscope and to be able to get the resources and the software they need. At this point, we've defined our STM32 USB device as a mass storage device. It's going to need a file system in order to communicate with the PC and share its files that it contains. We're going to place this file system on the STM32 internal flash. There are a few definitions that we need to update in order to tell the computer how big our mass storage device is. In this case, we're going to define a mass storage device of 64 kilobytes. We then update the USB device functions in order to include a memory copy function to copy information from our buffer to be placed into the STM32 USB peripheral and sent to the computer. So now we're going to create our file system for the STM32 flash. So what we're going to do is create the image with our files in it and then export it as a binary, and we'll put that into our code. What I want to put on it is a couple files to help the user get started. So I have an about page that pulls up the GitHub link, and then we have a download software page so they can go download the software very easily. So we're going to put these into the flash, and I found that using a Linux computer was the easiest, so I've SSH'd into a Linux computer here. And I'm going to copy these files over into our Linux share. I'll just make sure they're there. So in our share folder, we'll list our files. We'll just go into files. So there's all our files right there. We're going to get started with creating the image now. So the first thing we're going to do is to use this command to create ourselves an image of size, I'm going to say 64K. So we have our sector size of 1K, and then we just make that a count of 64K. And then we're going to fdisk into this image so that we can change different partitions and stuff. So it already created a new disk label for us, so we're going to type N to create a new partition. We hit P for primary, and then give it the default settings. And it said it created a partition 1 of type Linux, and we wanted it FAT12 for our little tiny file system. So we're going to hit T to pull up our options here, and then if we hit L, then we get a list of all our different codecs. We want it FAT12, and that's number 1, so we'll hit number 1. Just changed it to FAT12, and then we hit W to write the partition table. The next thing we have to do is to actually mount this device. We're going to use the loopback devices on the computer, so if I type in loosed up, I think is how you say it. You see our different loopback devices. I've already unmounted loop 0 from Snap so that I could use it. So now we're going to connect our loopback device to, so there's loop 0 to our flash image. I'll hit enter, and then we're going to make a file system on this with the name scope. So STM32 scope. You can see it created that file system successfully. And now we're going to mount this device to an actual folder. So I have a mount to FAT12, so it's going to go there. We'll copy our files now with this command. So we'll copy recursive files, and then the asterisk means to not copy the folder, but just everything that's inside of it. And then we'll move that into our mount directory. And we can go check to see if it's all there. So I go sudo. And so we can see everything's there, which is perfect. We'll go back out. We can unmount our device now and disconnect our loopback device. So unmount our file system, disconnect our loopback device, and now we're going to create the C code output. So we have this command, it's xxd-i, and then we have our flash image to our C code file. So here's our output right there. If I click on it, I've already created some other versions of this file system, so I'll just copy all that and go to my flash image.c, my STM32 cube IDE, and I just paste it in there. As for the file size, it's going to be the same in this case, they're both 64K. But that's how you create the file system image. I have my oscilloscope connected to the computer with an ST link, so we have our debugging pins connecting here, and I have a USB connected without power so we can see how it interacts with the computer. But before I get into actually uploading the code, I wanted to show you a few things. In order for it to sit at the alternate location, and the default location where the bootloader jumps to is 0x08000000. And that'll be our primary firmware because it's been linked to run there. We're going to run our secondary firmware at this location, which is 8010000. that corresponds to the next page after the finished page of the other device. So we changed that in linker script to place it in that section of Flash. And there's one other thing we have to do, and I'll show you that in just a second. We're going to upload the code now. All right, so it says that it jumped to the haul init function, which is great. And if we start stepping through the code, we'll see that it goes to some address that we don't know. But in regards to our vector table is not in the right place. So I'm going to actually edit it to put the vector table in the right place. So now if I continue running the code, we can see that it actually runs like it's supposed to. So we get stuck. If I pause it, we get caught in the haul tick, which is great because right here we have a pin toggling, and I can throw a breakpoint right there. There we go. It'll stop at the haul delay every 1 second. We have to set the vector table in order for the microcontroller to know where to jump when there's interrupts or whatever. So there's different things that it needs information to. So we have to set that vector table for it. And that's one thing we're going to have to do when we modify the primary firmware. In building our primary firmware, before we get too far into the weeds, I wanted to go over a flowchart overview of what's going on. So our code first goes to the entry point of the primary firmware, and inside of the primary firmware we're going to patch it around this part. But the code will initialize as normal, and then we're going to jump out of the original firmware and go to a function down at the bottom. We'll place it in the bottom of that original firmware. And it will check to see if PC12 is set. If it's not set, it will continue the firmware. It'll just jump back to the spot it left off. And if it is set, we're going to set the vector table address and then jump to the address of the secondary firmware. Now, this code kind of works. The problem that we have is that interrupts from the primary firmware, which have been initialized here, are still being triggered in the secondary firmware. So you have a bunch of pending interrupts that can't be serviced because their interrupt handlers aren't there anymore. And so your systic interrupt gets held up and never gets serviced because it's the lowest priority. So that means in our secondary firmware, the LED does not blink, and that's an important thing. And I definitely wanted to do it the right way. The second idea was to avoid this initialization process of the primary firmware altogether. And so we can go right from the entry point, enable the GPIO-C clock. Then we can check to see if PC12 is set, continue the firmware where it left off. If not, if it is set, we'll do the same thing, set the vector table address, and then jump. This doesn't work either because for some reason when we try to set the GPIO-C clock right after the entry point, it doesn't let us. It just returns the default value of the GPIO-C clock. I'm not sure why this happens. If I did a little more research, I'm sure I could figure out how to initialize the program in such a way that it could get past this. But I decided to go about this a little different route. This is the third solution that I came up with. I'll get to this part in just a second. The code, the primary firmware is going to initialize like normal. We'll check to see if it's going to jump out and check to see if PC12 is set. If it's not, it'll continue. If it is set, it's going to set a flag in the backup registers and then trigger a software reset. So now all the registers, all the interrupts, everything have been set to the reset state except for the backup registers. We go back to the entry point. It checks to see if the backup register flag is set. If it is, we're going to set the vector table address and then jump to our secondary firmware. And this is actually the working code. I'm going to show you how to program this in assembly with GitHub to patch the different instructions. I've got GitHub open on the left as well as my binary on the right that we want to disassemble. So I'll just drag that in there. And for the language, we'll just do Cortex for the STM32. And we'll be a little Indian. Well, we'll go ahead and analyze it so it can break down the binary for us and see the decompiler. It says that it's found the entry point, so we can go ahead and go there. This is where we can see our program sets the stack pointer and does the initializations that we would usually find. So the first thing that I'm going to do here is I'm going to increase the space of our binary. So if I scroll down to the very bottom, you see there's a certain amount of zeros here, and I'm going to increase this so we can have a little more space to put our program in. We can do that by going up to Window and then Memory Map. We can see our memory. It says it's in RAM. I don't really care to change it. We can press this button to increase the size. And we'll change this new address to be F900. And if we go back to the entry point, we can do that by going to Navigate, go to an entry. If you remember from our flowchart, we need to first jump to a function in order to check the flag. But before we program all of that, I want to program the part where we actually check to see if PC12 is set. And so we're going to need to know when it's done initializing. It's really nice that we have some recompiled code here. If I go open up my Cube IDE, you can see I've followed through the code until I've gotten to this PRV port start first task. And we can see right here it has an SVC0, so it does a supervision call, and then we'll go into the supervision call handler up there. What's really nice about this is that at this point everything's initialized, the RTOS is ready to start. We can just go search program text, and we'll just search for SVC. We'll do all fields, all blocks. We've now found our code that proves to us that everything's initialized and that our RTOS is ready with our SVC call right here. And this is the same code that you'll see in our recompiled firmware right there. At this point, we can navigate back by clicking on the incoming references. We can see this is the point where it would branch to that function. So instead of branching there, we're actually going to branch to our custom function. I'm going to make a function called checkPC12. I'm going to put it at F874. I'll create a label here by typing L, and then we can type our label. So I'll do check PC12, and I'll go through this in just a second. But before we do that, I'll go back to our SVC call. We'll go back here, and instead of branching here, I'm actually going to copy this. We're going to jump to it later, and we're going to patch this instruction, and we're going to have this jump to check PC12. And then right here, I'm going to create a label for the return address. Alright, so here's where we actually program our function. We're going to need a couple different resources in order to know how to code this. The first thing is we're going to need the reference manual here, and this will give us information about different registers and stuff, so we can see it has different locations for where the registers are located. The second document that we're going to need is the programming manual. See, this is where it gives us information to all the different assembly instructions that we can use. It'll tell us how to use them. And so I already know the addresses, and so I'll just hard code them in right now. You could hard code the addresses into instructions, but I'm actually just going to put in values that the computer's going to grab later. I'm going to navigate down to F8C8, and we'll make a bunch of unassigned longs here. So the first thing that we're going to need is the GPIO-C input data register address. And this is how we're going to get information about the pin state of PC12. And that is located 480000810H, or hex. And I'll go ahead and just hard code the rest of them in. We're now ready to program our check PC12 function, and we'll load into R0 the address of our GPIO-C input data register. The next instruction we're going to do is load into R1 the value at R0. We'll compare the two in order to get a result to see if PC12 is set. We're going to do an AND operation between R1, which is the GPIO-C input data register. We're going to compare between R1 and 0x1000, which is an AND operation between this register and the corresponding bit for PC12. If that's true, we're going to get 0x1000, or we're going to get 0. Next, we're going to do a branch if 0. I'm going to check to see if R0 is 0, and if it is, we're going to jump to another function, and I'll finish that in just a second. We're going to put our other function at F898. We're going to jump to the primary firmware. I'm going to do an isolation barrier just to make sure everything is set up correctly. And then we're going to jump to the function that we didn't jump to before. So that was that check PC12 that we didn't jump to. So we're going to branch link into that function that we didn't end up jumping to. And after it jumps to that function, it's going to branch link back here. And so we're going to have to jump to our return address. We'll branch link to our return address. And now up here, we can program our branch if 0. So if PC12 is high, then we're going to want to set a flag and do the software reset. And in order to set that flag, we need to set a bit in the power control register to allow us to enable or to edit the bits in the backup registers. So we're going to load the value of the power control register into R0. We're going to move the value of 0x100 into R1. And this is the bit corresponding to the bit that we need to set in the power control register to allow us to edit backup registers. We need to store this back into the power control register. So we'll store R1 back into the power control register, which is stored in R0. So we've enabled our bit now. Now we're going to load 1 into R0 so that we can set that bit. R0 now contains the value of 1. We're going to need to load the value of the backup register in order that we can store that into it. And then we'll go ahead and store that value. And at this point, we need to trigger a software reset so that it'll reset the program and all the registers and everything. And now check that flag to see if it's set and jump to our secondary firmware. In order to trigger the software reset, we need to load the address of the AIRCR register. We're going to load into R1 the value of our software reset key and reset bit. Now we're going to store the value of R1, or that reset key in bit, into the application interrupt reset and control register stored in R0. And I'm not sure if the software reset's done immediately, but I'm going to just sit in a loop until, and so I'll just create a label called loop, and then we'll just branch to loop. All right, and our jump to primary firmware is all done and everything. So now we just have to program the function in which we check the flag and jump to the secondary firmware. So if we now go to the entry point, we can replace this first instruction with the jump instruction. But the struggle that we might have with that is this piece of data where we set the stack pointer will now be overwritten. Now I've already got this value, this substitute value stored right down here. So right here, we'll create that check for flag function. In order to do that, we'll load the value of the backup register into R0. We'll load the value at that register into R1. We're going to branch if not 0 for the value in that register. I'll create that function now because we kind of need it. All right, and we'll get into creating this jump function later. And if it is 0, we can continue with the firmware as normal. And so we can now, that instruction that we didn't do before, we're going to load wide into the stack pointer register, that substitute value. And then because we branched here, we can just branch back to the link register. We can now change this initial instruction to branch to our function check for the flag. So the very first thing that the program will do is check for that flag. If it finds that flag set, it'll jump to new firmware. Now we'll actually program the function to jump. So the first thing we're going to need to do is to get the value of the base address. We'll load that into R0. This is the address for our secondary firmware. We'll place that in R0. Then we're going to load into R1 the location of the NVIC table register. So we need this register address in order to set the NVIC table. We'll store R0 into the NVIC table, set the stack pointer so we can load register wide stack pointer, and we can get the stack pointer out of our NVIC table. We're going to load into R0 the address that we actually need to jump to. And so we'll get this from the vector table. So this is the address of our entry point. And the vector table, this is located 4 away from the start of the vector table. And now we can just branch to the address. All right, so this is our finished code for our patched binary, and this should jump to our secondary firmware, and we'll see how it works. So I've uploaded our new firmware. That's our patched primary firmware as well as our secondary firmware acting as a mass storage device. If we flip this boot mode switch to the left corresponding to PC12 being set and turn on the power, we can see that it opens up our mass storage device. From here we can go ahead and download the software for our oscilloscope. When we're all done with that, we can flip this switch back and then power cycle the board. And it automatically opens up our embedded oscilloscope application. From here we can connect and use the different instruments that we have available. The reason why it automatically launches is because of this auto launch service that I chose to develop. It listens for USB events and then compares the VID and PID against known values, and then will execute a executable path. I find this especially useful for this oscilloscope, and I'm sure there's other useful applications for it as well. And as many configurations as USBs can be added to that configuration file. You can see when I turn off the power switch, it closes it as well. Thank you guys for watching my video. I hope that you enjoyed it and that you learned something. And all the resources for this project are linked in the description.